My name is Ivan Provalov. I'll be talking about the relevance improvements at Cengage. So the things I will cover today, I'll talk about the improvements at Cengage. I'll start with my background. I'll tell you about the company I work for, Cengage Learning. I'm not sure how many people have heard the name. And I'll talk about our search platform profile, and then some of the issues we've faced in the last couple of years, as well as what kind of methodology we use for relevancy tuning, and then I'll jump into a few implementations we did on English content, as well as non-English content. So I'm an information architect with Cengage. My background is software development, information retrieval. We're also hosting a Michigan Information Retrieval Meetup. And if you're interested in presenting remotely or online, you're welcome to contact me. We do it about once a quarter. Would be happy to hear your presentations. So Cengage Learning is about $2 billion annual revenue publishing company. We primarily focus on textbook market as well as library markets. We have research databases, about 600 of those that we sell to the libraries. For our reference data, we publish a lot of encyclopedic content. At any given time, we have about 10,000 contract writers writing for our encyclopedias and reference materials and other publications. Our brands include Gale, Brooks Cole, Course Technology, etc. We also recently acquired National Geographic School Publishing, and we'll be unveiling a few learning products. We have about 15,000 different publications that we also act as a broker to all these different publications like New York Times. So there's a lot of periodical content that we ingest and then we provide in our search products. So I'll give you some couple of different slides of our product snapshots to give you an idea. But our search platform profile is it's a custom Lucene-based implementation. We support about 100 products. Have pretty complex rights management system. We have custom products that are that put a lot of load on the system as far as creating filters. So to give you an idea, out of those 15,000 publications that we ingest, in a lot of cases, customers can go on and pick and choose any combinations of those to create their custom products. And we have to create a custom filter for that at search time. And so you may end up with about like 10,000 filters being created on an hourly basis. We host about 210 million documents. We host them, so the setup is similar to like Solr. We use shards. We have about 18 shards at the moment, about 150 index fields per shard, and about 21 million terms per shard's full text index. And so our load is about 250 queries per second at the moment, and it's growing. At the moment, we're going through the peak times as our primary users are students that are sitting at libraries right now getting ready for final exams, their midterm exams. So we have a couple of peaks per year, November and then April. So Gale Virtual Reference Library is it gives you an idea of different, the subjects on the left here. All these encyclopedic type and reference type materials. We have Encyclopedia of Medicine, historical, law-related stuff. Or here we have completely different type of product where this is a portal and you have all these different genres aggregated to the same screen. A lot of times, actually even different searchers are being run on the back end to produce this type of screen. You can see on the top like viewpoints, and then followed by images, followed by news. All these are different genres, and a lot of times these will be done by different queries to generate screen like that. So again, these kind of products will put a lot of load on the system. Here's our MSG group that does searching, and I just want to share with you. So it's a real fun environment to work in, agile. We use test-driven development and pair programming. So jumping to the relevance issues that we faced, there's 4 categories of different issues I would like to talk about. The first one relates to the ranking itself. For some products, it's important to have very current content, And so the recency is obviously a concern. For some other products, it's the actual publication itself that has to be ranked with different weight because of the importance of New York Times comparing to maybe a local Florida newspaper is much different. Then we have some document length concerns. For example, Leucine will boost shorter documents, but in some cases, those short documents may not be good for some products just because of the content type they have. Another issue could be unbalanced shard, where you have a sharding strategy. You could have a sharding strategy where you could be just loading shards in chronological order, but then relevance may be skewed based on chronology or maybe skewed based on the number of documents per shard. So that's another issue. Zero results query is a big concern. You can always find that information from your logs, but those are the queries that don't return results. Definitely worth looking into. And I'll talk about how we're addressing that. Also content quality related stuff. So this one I'm not going to talk in detail, just a couple issues related here. In multi-million document system, you always may end up with some duplicates that you don't know about. And some of them may be completely legitimate duplicates, like financial statement of different companies, or the same company may just have numbers changed, and they're still very close in their content because line item descriptions are the same. But these are good documents, nothing wrong with them. But in some cases, content coming into the system may be duplicate in part, and those could be damaging to your specific product. And so it's also worth investigating. Then we also have a lot of products use our digitized content that comes from 18th century collection, 19th century collection, and then when you OCR that content, the more back you go, the less image quality you have, and then OCR quality suffers, and you have character recognition issues, and so that type of content produces a lot of garbage terms. And so when I mentioned the term 21 million terms per shard, we estimate about 8 million of those are produced by this OCR content that are just garbage terms, and we're dealing with that as well. On the language side, of course, there is tokenization, and then there is language detection at search time if it's required by the product. So I'll talk about the relevance tuning. We use the TREC text retrieval conference data. So the way it works, text retrieval conference is held once a year. So participants normally are given certain tasks, and then they submit their runs, and the data is pooled together, and then there's certain manual annotation going on. So as a result, they produce some good judgments for a set of queries and specific content. So what we do is we buy the collections that are used by TREC. We also get the judgments and the queries themselves. And it allows us to establish a baseline for, first of all, how our system performs on that particular collection comparing to other TREC participants. And secondly, gives us a baseline that we can run in the future against. When we introduce a relevance improvement, we want to make sure we didn't actually made some other improvements worse, or we didn't make the overall relevance worse. So that gives us some first step in the relevancy tuning. And we use 3 main metrics here: precision, reciprocal ranking, and recall. So for the precision, you probably know it's measured at the relevant document. So let's say if at the position 10, the number of documents relevant to the query was 4, then your precision is 40%. Average precision is when you average all these numbers until a certain cutoff point, and then the mean average precision is when you take average of multiple queries. So that kind of gives you like a single number to go by. And then reciprocal ranking is when you get your first relevant result, say in the position 3, your reciprocal ranking would be 1/3. It's a reciprocal number of the first relevant document. And again, you average it out over a number of queries. Now, recall is different. You'd have to know how many relevant documents you have in your collection to measure recall. So recall is the number that tells you how many of those relevant documents you actually retrieved. And it's really tough to do without knowing your content really well or without having some controlled collection, and that's where TREC helps a lot. But I would like to also mention that this is not our main measurement or main methodology. We're focusing mostly on internal studies of the top results. So TREC is a really fine tool to use, but it boils down to your content and your queries from your logs to tune your system relevancy. And so for that, we do a lot of internal studies ourselves. So what we do for that, we grab top queries as well as long tail queries specific to a product, and then we sit down in the room and we evaluate those results. And we focus on the top results because of the cost of that process is pretty expensive. We also do outsourcing to local universities. Recently, we've done work with Wayne State University in Michigan, and the School of Information and Library students would actually do similar things for us. It helps because these are the students that are kind of similar to our end users because of our library products. So I'd like to show you this relevance evaluation form. That's what we typically would use. It's a brief, well, it's a complete document retrieved, and then there's a scoring on the bottom where you can evaluate, and we use four-way evaluation, which is if there's no documents returned, it's 0, and then not relevant, somewhat relevant, and very irrelevant. Now, the system is kind of flexible, so we can set up different scaling and different scoring. So we're still experimenting with that. Then what we would produce in the end of this experiment, we'll go over the pool of about 50 queries broken down into these main categories, and then we'll look at the bottom line and see whether the improvements we introduced in this particular case worked or not. And so in this case, you see that we've picked mostly top 100 queries categories, and they all further break down into like frequent expressions like Civil War or person, place, work. Those are the commonly used queries for our reference systems, or single term queries from the top 100. And then we also look at the long tail queries that primarily return 0 results, and that's what the focus of these top 2 items. So misspelled ones and multi-term queries. We also focus on the usage data reporting. So from the usage logs, we get those top 100, of course, in the long tail queries. But we also look at some of the session and query information. So this screen kind of gives you an idea. This is one snapshot of the session summary type of reports that we do. Like we measure duration, the retrievals. We look at the number of retrievals, click-through rate, and so on. And then we also look at the 0 results queries, and we'll look at the average number of terms in the query and so on. So we have about at the moment we have about 15 different reports. So now I will talk about 3 major categories of the relevance improvements we've done. Again, for the sake of time, I won't have a chance to cover all the things that we're looking into, but these are the main I would like to share with you. So I broke them down into pre-processing and then search time and then post-processing. And these are all basically search, not index-related improvements. For the pre-processing, we have a search assist tool, and it provides recommendations of the search terms. It attempts to do a spell correction as well, and then provide the right or recommended query, rather. We use commonly occurring phrases, so it's a term collocation based, and it's based on our content itself. So we take our 200 million documents, we run it through the term collocation, we create these dictionaries, and the complexity is that we have to do it for each specific field separately. Like we have a keyword index, we have to create a dictionary for that index separately from, like, say, title index. And it's also complicated by the fact that when the user actually searches, they search specific content set. So it could be related to a particular product or a custom product, but they have to be filtered for that particular product. So all of that applies to all the terms in the search assist tool. Then the next category, we have term query expansions. And I'm listing here these three: the stemming, spelling, and pseudo-relevance feedback. So as far as the stemming, we decided to go with what we call dynamic stemming approach. It's different from, like, let's say, traditionally you would do, during the index time, you would stem each term, and then you store it in your index. And that has its own advantages, because that way you can actually reduce your index size, and it's probably faster search as well. But disadvantage of that static approach is that if you have a requirement to maintain both stemmed and unstemmed index versions, you end up with creating maybe a duplicate for each field that requires stemming. You could alternatively probably put your stemmed terms into your unstemmed index and just have one large index of both. What we decided to do instead is we decided to create this map of stem families. So for a word like water, a parent is water, and there's a certain number of like children terms, like water is watering, watered. If you stemmed any of these three, they would result into your parent term. So when at search time the term comes in, we stem it first, we look up its parent, and then we expand it with these three terms in the case of water. So what it allows us to do is a couple of things. I think we're saving actually on the index size, because we do have a requirement to maintain both stemmed and unstemmed search. And also, if we decide to switch to a different stemmer in the future, it will not require a reindexing of the entire content. So we think that this approach should work best for our situation. The next one is the spelling. And we use a couple different dictionaries. We have a base dictionary that's kind of similar to like Linux dictionary, and then we have expanded one that is generated by our subject classification system, and it's more controlled vocabulary. So, and it's more tuned to our collection. When we do few different expansions, we normally skip spell correction. Like, for example, for a phrase expansion queries, we would not do spell correction, because that introduces certain problem with like how to create Boolean clauses. But then the approach is similar to spell checker in Lucene. It uses Leucine distance to look up the terms. For pseudo-relevance feedback, it's one implementation that we have not completed yet, and there's the primary reason is the stored term vectors. They do add to the size of the index, and the way our workflow is set up, we do certain copying of the index, and that kind of would slow down our copying step, and it could make the system go outside of the range of the time we need to process everything. So to give you an idea, we turned on the stored term vectors on our index of about 10 million terms, and that resulted in an increase of from 24 gigabyte to about 38 gigabyte in size. We haven't done other tests yet. This was to turn on all stored term vectors as well as the positions. So if we turn off the positions, it could actually go smaller. But at the moment, we're dealing with that. What we noticed, however, based on our TREC tests, that pseudo-relevance feedback gives you a huge improvement in relevance. I mean, we've seen like 70% improvement in just mean average precision. So that's why we're persistently pursuing this route. The next category is phrase query expansions, and there are a couple different things here. Especially in the library market, there are certain expectations to provide answers. You know, when somebody's searching for like capital punishment, to find death penalty and vice versa. So by our upstream systems that process our content and classify it and create keywords, subject keywords, they call those terms non-preferred terms, and we typically don't put them in the index itself, because not every product has that requirement. So what we do instead, we do, again, dynamic lookups for these kind of terms. So again, the upstream system is the one that hits all our content before it even gets to the search engine. And they do a lot of pre-processing. They do entity extractions, classification of the content, and they do it with machine-aided indexing tools like Verity and NetOwl. But then certain content undergoes through the manual indexing process. Like we have reference materials that are very valuable, and we actually will have a human being to go through the content and injecting the subject key term words. And so a lot of that information is very valuable. We found that just injecting subject terms into our catch-all index gives us about 20% boost for just mean average precision boost. So the second one, the phrase extractions, is meant to deal with the zero results queries. So if you have a query that we think if it's longer than 3 terms, and you're using AND operator, so you're trying to narrow down your results, it's a high precision query, that query is unlikely to return results because of the constraints you're applying. So what we try to do with those queries, we try to extract phrases based on the part of speech patterns. So like in this case, if it's like an adjective followed by noun and then plural noun, like in the case of this query example, you would actually extract this phrase, Afro-American traditions, out of the longer original query, and then you would OR it into the original query. So what happens is, if the original query does not return results, when our typical product would do some failover mechanism. What this meant to do is to actually reduce that failover and assume, okay, if you're 3 terms long, you're probably not going to return results. I'm gonna throw this good phrase into a query, expand it, and then get results back. So what we've seen so far, we take our zero results queries from the logs, and we analyze them. We throw them through this phrase expansion. It seems to work well, and it increases our results for the internal studies from what we've seen. So the next couple of modifications we've done is based on the function queries. If you're not familiar with a function query, it's described very well in the Leucine in action. It's actually chapter 5 talks about the recency boosting. It's a real good example. I recommend, and our example, our implementation basically follows that. It's based on the fact that certain products want more current product, and it's really a simple implementation based on how recent that document is. And we expose certain things to our products. They can actually specify the multiplier by how much they want it boosted, the date range, and so on. So the recency boosting provides more current results on top. The publication boosting is similar to recency as far as the implementation goes, and it's also using this function query. It comes from the fact that you have certain content like New York Times, again, that is just more important to show on top. And so we have this publication list of importance ranks, and these ranks or scores are assigned to each publication. And a lot of different stuff that goes into deciding what score to assign. So there's a whole process around that. So they analyze clickstream information, so how many times that publication was hit, and how many products we use that publication, whether publication is peer-reviewed, so it's the quality of the publication as well as other factors. And the bottom line, again, you're actually providing a mechanism for the products. We're exposing, again, this boosting factor and say, well, by how much you want to use this specific boosting. So the next category is results clustering. And here I'm showing 2 examples. I have subject index-based results clustering and then dynamic approach with caret 2. So the subject index, again, it's that machine-aided indexing generated from the classification tools like Verity. And what you see here is this is typically our left sidebar that shows the subjects with the hit counts, and that allows users to navigate through the content. The reason we're looking at the dynamic approach like caret is because our high-quality subject indexing, it took us a few years to actually create that kind of system that has good vocabulary, good business rules. It's based on a rules engine to actually generate and inject those subject keywords into the content. If you go to a foreign language, if you go to Chinese, you'd have to create that same system from scratch. And so that's where the dynamic stuff like caret 2 comes in. And I showed my favorite visualization here, the foam tree. The idea is similar, but there are certain differences between your metadata-based clustering and your dynamic clustering. The number of results, you cannot cluster your entire content and say, or your entire result set. Say, for example, we're pulling back 3,000 results with Caret. It's probably not going to work well. In fact, it works best under 1,000 results. So if you want to retrieve 3,000 results, you want to cluster only a certain number of them. And we typically go under 1,000. And it also introduces a little bit different load on the system because now instead of retrieving a page worth of documents, you want to actually fetch back more than a page. But there are ways around that. So what we do is, for example, we're not throwing the entire content of a document on Caret. We're only using like either summaries or even titles, and even that works well with Caret. So highly recommend. The next thing, I want to talk about 3 different languages that we've experienced, that we experimented with. Spanish is the first language. We currently do have Spanish content in our system, and we don't use Spanish Analyzer at the moment, right? So it's a standard Lucene analyzer that actually has one tweak in it. It does fold ASCII characters. So it deals with diacritics, but it doesn't have things like stammer and stop words as the Spanish Analyzer does. So on the bottom, I'm just showing some of the scores that we've, when we compared Lucene Standard Analyzer without any stemming or stop words and compared it to the Lucene Spanish Analyzer, you do see the improvement, and it's definitely worth switching over. Now, when we experimented with Spanish collection from TREC, some of the things to look out for, whether it's English or non-English content, is encoding. And this is, you want to make sure everything is encoded in UTF-8. So you want to probably, the first step is to convert everything, because you may see some very inconsistent results. The next collection of data was a little bit more complicated. It's Arabic language. The researcher that we've hired for this project was a native speaker, and that helped with understanding some of the underlying issues. But we also did just a benchmark. We compared Lucene Arabic Analyzer with Standard Analyzer, and the results are more different when you compare like Spanish language. So there are other things that come into play with Arabic language, like letter tokenization, that's basically dealing with all kind of different folding of diacritics. And of course, the stammer is probably the primary thing, because it deals with things like suffixes and prefixes and conjunctions and so on. And then the Chinese was probably the most complicated case for us, because Chinese is very different from when compared to English as far as character set. There's no white space, so there's a different tokenization strategy. You can also actually choose more than one sorting strategy. Like, say, if you want to sort by title, there could be a couple different ways. There's a variety of different encoding, and there's also highlighting issues. So when you want to do a term highlighting, it depends on your analyzer. So what we've done, we compared a few different analyzers, and here we're showing results of our mean average precision comparisons. And what we did initially was we went with a CJK analyzer. That was the simplest implementation for us. It was part of Lucene, and it worked well, and we started testing it with the end users. And then we found out that it had a couple different issues. One is it's using a bigram approach, where you just tokenize by bigram, and then at search time you're using the same tokenization strategy, and it returns results, and it works well until you come across a query which is only a single character, in which case you cannot even retrieve that. Another thing is for term highlighting, if you're just using bigram, like two characters next to each other, tokenization strategy, your term highlighting simply won't work. So the analyzer that we ended up with is Powding, and that kind of solves both issues. The implementation is a little bit more complex. It includes a dictionary that you'd have to load in runtime, as well as the indexing. But it does address both of those issues. It's highlighting the right terms, also deals with the unigram characters. So in conclusion, I would like to say that Lucene relevance ranking is pretty good, but you also have some opportunities to tune. There's a lot of tools that are provided that you can tune relevance. A lot of times simple techniques work really well, like stemming, pseudo-relevance feedback, recency boosting with function queries. Language-specific analyzers are definitely worth time investment, and they will work better than standard analyzer for those particular languages. I also recommend to use TREC collections because it helps you create the baseline and helps you to make sure your relevance is not slipping. And then relevancy priority in your search system development has to be probably on the same level as your code quality or system performance. So thank you very much. Questions?
You said you're using a subject area based dictionary. So can you expand a little bit on that?
Yeah, so we create dictionaries by pre-processing content before it makes it into our search system. And we use tools like Verity that classify content and then produce certain subject keywords for us, right? So then you can take those terms that, say, are typical for that class, and then we put them in the index. And that's what, and then from that we also create a dictionary that we use for other things. The question was whether we use that dictionary at query time. Yes, we do use that at query time as well. We actually do both. So the subject terms that are produced are kind of, they fall into several different categories. We do classes of subjects that are like preferred versus non-preferred terms. So non-preferred terms are typically done at search time. But preferred terms will be put in the index.
Could you explain a bit how you deal with duplicates?
So the duplicates is not a completely solved problem yet, but we think we have a solution for that. So the way we deal with them is we run each document through, we create a signature for each document of terms. So initially we looked into using shingling for that, to create like a signature for, not even a signature, but to create shingles first and then start comparing shingles. But it seems like shingles create much larger index, obviously. So we're creating a signature for a document of the best TF-IDF terms. So we take TF-IDF, we sort them, and the best 10 terms, for example, create your signature for a document. And that's kind of like a first run through. And then we group them, we put them in the clusters of documents. Then once we're in that cluster, we'll go through each cluster and then dedupe at that level, doing more intensive comparison. So with that, the only problem is that when you have multiple shards, you have to get those clusters and probably merge them at some level and then do the final step.
Could you explain the search assistance in more detail way?
So the search assist, what kind of detail? I'm sorry, what kind of details were you interested?
Like, is it something really standard, or you have developed your own framework or techniques?
Yeah, so the search assist dictionary itself is completely custom created system. It's based on term collocation idea, similar to Mahout term collocation. If you decide to go with term collocation approach for search assist, I would definitely recommend to use Mahout at the moment. So there were other reasons why we went with the custom approach, but Mahout term collocation can create pretty good dictionary for search assist.
I see that you have factored in the time duration in your relevance factor, as if like say yesterday's, if it appeared yesterday, maybe it's less relevant than what if it appeared today. Was that formula arrived at based on some empirical studies, or how did you arrive at that formula? I just recall that you showed some formula on that.
Well, so the formula for the recency is proportional to how recent the document to certain date in the past. And products can actually, there's no set formula at the moment, right? We have some default value, but we don't think we have like the final answer. So we expose that to the products. And when we test that for the particular product, we can actually still tune that. So we can still tune that range and also that multiplier that we provide. So they can actually say, well, boost that a lot or boost that a little bit less. So at that time, we can go with the final tuning.
Do you use the Lucene benchmark tools for running the quality benchmarks?
Yes.
And what is your experience with that framework?
So we do use Lucene benchmark tools for TREC experiments pretty extensively. We participate in TREC, and of course for our internal testing, we do that. We've had good experience with that. With the past TRECs, sometimes you'd have to change the format. Well, not the format. You have to change how you ingest, like judgments or queries themselves, because the format have changed over the past few years. But that's about it. Everything else we found is working really well.
All right. You mentioned multilingual processing, but you only talked about the Chinese. Did you try with other languages, for like, especially with other CJK languages like Thai or Japanese, or did you try that?
Oh, you mean like carrot with other languages?
No. I mean just relevance judgments and everything and all that. Was it just Chinese that you experimented with, or did you try with Japanese? Because I know there are a load of other problems with Japanese in particular, different writing systems and stuff.
Yeah, so for English, Spanish, Arabic, and Chinese, we use TREC collections and judgments. For other languages, like Japanese right now, we're just starting to pick it up. There are other similar conferences like that. So we work with Japanese organization to get the collection. Because I mean, if you think Chinese is complicated, Japanese is probably another. Yep. Any other questions? All right, thank you.
Thank you very much.